Welcome viewers. In this video we'll see the AC terminology. First we'll see the waveform. The waveform is nothing but the graph drawn between the alternating quantity with respect to the time. The waveform is the important term in AC terminology. In case of DC, the voltage or current is always constant, direct current, always constant irrespective of the time. For the given time, for any time, the voltage is constant in case of DC. But in case of AC, alternating current means it is keep on alternating, that is changing from positive to negative with respect to time. So the waveform is very important in case of AC terminology. The alternating quantity may be either voltage, current or flux. We can take either voltage or current or flux. There are so many type of waveforms available. We will see these waveforms one by one. Let us assume that the alternating quantity is voltage. The alternating quantity may be voltage, current or flux. Here we assume that we will take the voltage as a reference. First we will see the sinusoidal waveform, sine waveform. So this is a graph drawn between time and voltage. You see that from 0 to pi the voltage is positive. From pi to 2 pi the voltage is negative. So we have positive cycle and negative cycle, alternate. The voltage is alternate between positive to negative. From 0 to pi means 0 to 180 degree, the voltages keep on increases, reaches the maximum value, again decreases, again reaches the 0 value. It is in terms of sine theta. The increasing and decreasing the voltage is a function of sine theta. So that it is called a sinusoidal waveform, sine waveform. From 180 to 360 degree, same thing repeated, but it's a negative cycle. So that positive and negative voltages are keep on changing, so that it is called a alternating quantity. Alternate means positive to negative, negative to positive, like that it will go. So due to that it is called as a sine wave, as a alternating quantity. We will see the some other waveforms, triangular waveform and rectangular waveform. This triangular waveform, it is in the form of triangle, so that is called a triangular waveform. From 0 to pi the voltage is positive, pi to 2 pi voltage is negative. That is voltage keep on increases, reaches the maximum value, then decreases, again reaches the max 0. The same thing repeated in a negative region, negative voltage. It is look like a triangular, so that is called a triangular waveform. Then we'll go to the rectangular waveform. The graph drawn between time and voltage. From 0 to pi the voltage is positive. From pi to 2 pi the voltage is negative. So we will get positive voltage and negative voltage. So that's called a alternating waveform. It's look like a triangular. It's look like a rectangular. So that is called a rectangular waveform. So alternate means positive cycle and negative cycle keep on changes. We'll go for some more waveforms, sawtooth waveform and trapezoidal waveform. So sawtooth waveform, it look like a sawtooth, so that is called a sawtooth waveform. So here the voltage is maximum, then reaches the 0 value at 2 pi. Again from 2 pi to 4 pi the voltage is again maximum and reaches the 0 value. But here the voltage is always positive. So this is not a alternating quantity. This is a non-alternating quantity. Alternate means the positive and negative will change continuously. Positive cycle, negative cycle, positive cycle, like that. But here always we have positive voltage. So this is only this waveform is a non-alternating quantity. We'll go to the trapezoidal waveform. It looks like a trapezoidal. So that is called a trapezoidal waveform. 0 to pi we have positive voltage. So initially 0 increases, reaches the maximum value, then constant for some time, again decreases, reaches the 0 value. Same thing repeated in a negative cycle from pi to 2 pi. So we have positive and negative. So that's called a alternating quantity. So only this waveform is a non-alternating. The remaining waveform also are all alternating waveforms. Now we'll go to the remaining terms of the AC terminology. The remaining terminology we'll explain with this diagram. Now we'll consider the sine wave, sinusoidal wave. The waveform vary with the sine theta, so that is called a sine wave. That is sine 0, sine 90, sine 180, sine 270, then sine 360. Like that is keep on changes. The sine of theta, so that is called a sine wave. Is drawn between time period and voltage. See, at 0 degree the voltage is 0, then keep on increases, reaches the maximum value. That is here sine theta equal to 0 degree, here sine theta is 90 degree. In between it varies from 0 degree, 10, 20, 30, 40 like that. Thereafter again decreases and reaches the 0 again at pi 180 degree. Then same thing repeated in the negative cycle. Again the waveform increases in the negative region, reaches the maximum value, then decreases and reaches the 0 value at 2 pi 360 degree. So from 0 to pi 180 degree the voltage is positive. It's called a positive half cycle. From 180 to 360 we have negative voltage. So this is called a negative half cycle. The sum of these two, positive half cycle and negative half cycle, is the full cycle. The full cycle is nothing but sum of positive half cycle and negative half cycle. This is one cycle, changing from positive to negative, positive quantity to negative quantity, completing the positive quantity to negative quantity from 0 to 360 degree is called a one cycle. In that we have two. Up to this is the positive half cycle because it is half of the waveform, so that positive half cycle. This is remaining half cycle, so negative half cycle, right? So the cycle is nothing but completing one positive as well as negative voltage, that is up to 360 degree. In that we have positive half cycle and negative half cycle. So this is the nothing but time period. The time taken to complete one full cycle, that is positive as well as negative. The time t is nothing but the time taken to complete positive cycle as well as negative cycle, one complete cycle. The frequency, you know that frequency equal to 1 divided by t. The number of cycles per second that can be calculated 1 divided by t. T is nothing but time period. So what is amplitude? The maximum value is called the amplitude, where it is available at pi by 2, that is sine pi by 2, sine 90, we have maximum value. So this is the maximum value. Amplitude is nothing but maximum value. So here 0, then keep on increases, at this point only it reaches the maximum value, so that this amplitude is nothing but a maximum value. This value is nothing but a amplitude. Now we'll see this one by one. What is cycle, what is time period, what is frequency, what is mean by amplitude, everything we explained with the diagram. Now we'll see the definition. Right. Cycle is nothing but it is a set of positive and negative portion of the waveform. One cycle means it is the completing one positive cycle as well as negative cycle. Then what is time period? The time required for an alternating quantity to complete one cycle. One cycle means positive as well as negative. Is called a time period. Is denoted by t. The cycle is nothing but set of positive and negative. The completing this positive and negative is called a time period. Then we'll go to the frequency. Frequency is nothing but 1 divided by t. The number of cycles per second is called a frequency. So cycle means positive and negative. So completing one positive and negative per second. Within a second, how many cycles are completed is called a frequency. It is denoted by F. The unit will be cycles per second or in hertz, or it is called a hertz. F equal to 1 divided by t. Then amplitude. What is amplitude? It is a maximum value. We already referred in the diagram. The alternating means the positive negative changes, the value also keep on increases and decreases. In that maximum value of the alternating quantity in a cycle is called a amplitude. The maximum value is called a amplitude. Already we referred in the diagram. It is also called peak value or crest value. Peak value means peak means maximum. Now we'll go to the remaining terminology. The next term is the average value. What is average value? See, the waveform keep on increases, keep on changes from initially 0, then reaches the maximum value, again 0, again going to negative. So values keep on changing. Average value means we need to add all the terms from 0 to 360 degree. If you add all the individual values, that will give the average value. That is a general. In case of alternating, what is the meaning? The average value of an alternating current, here we refer the current, is defined as the DC current which transfer across any circuit the same charge that is transferred by alternating current during the same time. So the average value in general is nothing but by adding all the value divided by total will give the average value. Similarly here also same, but the definition is DC current to alternating current. Suppose the DC current is transferred across any circuit. The same charge as is transferred by alternating current is called a average value. Right? One circuit is available, in that DC current is passed. For the same time, what is the alternating current is passed for the same charge is nothing but a average value. So what is the formula? I average. Now we are referring current. Voltage also we can take. 1 divided by pi, 0 to pi I d theta for symmetrical. What is mean by symmetrical? Positive and negative. If you have positive cycle and negative cycle is called a symmetrical. Right? The positive cycle same thing will be available as a negative also. So this is the symmetrical waveform. Here we have positive and negative. If you put one line here, this both the sides are equal. This is positive, this is negative. So that is called a symmetrical waveform. So in that case we can take only one cycle, only one half cycle, because next cycle also same. Positive cycle is very similar to negative cycle. Only the thing is the polarity will change. Right? So that we will take 1 by pi up to 180 degree. The limit also 0 to pi I into d theta. So this is nothing but taking the average from 0 to pi, each and every value we are integrated, so that we will get average. In general, average mean I1 plus I2 plus I3 up to In divided by n. Like that here we are doing integration, so that we will get the average value. So a symmetrical waveform means positive half cycle and negative half cycle are equal. So we can take only one positive half cycle, only one half cycle. No need to take the full cycle. So that it is 1 by pi, 0 to pi I d theta. In case of unsymmetrical means it's not a alternating quantity. Right? So here we need to take full cycle. It may be is a non-uniform. So that we need to take full cycle 1 by 2 pi. 360 degree. 360 degree only the one full cycle. Here we are considering full cycle. Here we consider only half cycle, because next half cycle also very similar, symmetrical. So 0 to 2 pi I d theta for unsymmetrical. Right? If it is symmetrical, we can take only half of the cycle. If it is not symmetrical, we need to take full cycle. So what is the current waveform? Current, the expression I equal to Im sin theta. So this current is vary with the theta. If theta is 0, current also 0. Theta is 90 degree, 90 means 1. So current will be maximum. 180 means again 0. 270 means minus. 360 means again 0. So based on the theta value, the I will changes. This Im is nothing but the maximum value. Maximum value. That's called the amplitude, maximum amplitude. So I equal to Im sin theta is the general waveform for a sine wave. The I varies with the function of theta. Now we'll go for this average value. We'll substitute this I as Im sin theta. Now we'll find the average value of the sine wave. So I average equal to 1 by pi, 0 to pi I d theta. Because of symmetrical, we consider only 1 by pi. So 1 by pi 0 to pi, I is nothing but Im sin theta into d theta. So this Im is constant, we'll take outside Im by pi 0 to pi sin theta d theta. So Im by pi, the integral sin theta is minus cos theta. That is, you need to substitute the limit 0 to pi. I will substitute the limit. So Im by pi minus cos pi. While substituting lower limit, one negative will be there. Already one negative is there, so it becomes positive. Plus cos 0. So cos minus cos pi, upper limit substituted, lower limit plus cos theta, cos 0. Here negative is there, while substituting lower limit, one more negative will be there, so it becomes positive. So Im by pi, the cos pi value is minus 1. Already one minus is there. Cos 0 value is 1. So that Im by pi minus minus become 1. 1 plus 1. So that's 2. So I average equal to 2 Im by pi. Right. So here 1 plus 1 2. So 2 Im by pi. That is nothing but 2 by pi is 0.637 Im. So the average value of current in a sine wave is nothing but 0.637 Im. But in average value, what is the disadvantage? We have one positive cycle and one negative cycle. If we add positive cycle and negative cycle, it becomes 0 because of polarity. One is plus, one is minus. So while adding these two, we will get 0. So for that, we can go to the root mean square value, RMS value. That is, the current is squared. While taking the square, what will happen? The negative become positive. Then we'll take square root. So the originality will not change. Right. So in the average value, during positive half cycle, the voltage is positive, but during negative half cycle, the voltage is negative. If we add both, it becomes 0. So that we go for the root mean square value. We'll see what is meant by root mean square value. So root mean square value, in order to avoid the average value becomes 0 due to positive negative, we'll go for the root mean square value or effective value. That is, while taking the square, the negative become positive. Again we are taking the root, so it become normal. So what is the definition? The steady current which when flowing through a given resistor for a given time produces the same amount of heat that is produced by alternating current. When the current is flowing through the same resistor for the same time is called a RMS or effective value of an alternating current. Again the definition is, what is the definition? The current is flowing through a resistor for a given time. At that time heat is produced. For the same time and same current, what is the heat produced in the when the alternating current is flowing? So this is the definition. The current flowing through the resistor for a given time, heat is produced. For a DC current, what is the heat produced? And for the same, what is the heat produced for alternating current? That is the definition. Now we'll see the waveform. We will see the equation. So again we have the unsymmetrical and symmetrical. Symmetrical mean we can take 1 by pi, only half cycle. Unsymmetrical mean we have to take full cycle, 0 to 2 pi. So here what we are doing, I RMS square equal to I square. Here taking I square. If you take square, what will happen? During positive half cycle, the current is plus I. During negative half cycle, the current is minus I. But while taking square root, it become positive. So it will not 0. Plus I and minus I will not 0. Both it become positive. So that we are taking square. So the negative term will be converted into positive while taking square. But again we are taking the, here also we are taking square, or we can take square root, so that the originality will not change. So here what is that? 1 by t 0 to t I square dt. This is a general term. T is nothing but the time period. It may be 2 pi or pi, or t by 2 means half cycle. So this is a general formula. The t may be 2 pi or it may be pi. Now we'll go to the alternating quantity. We'll see the RMS value. So I equal to Im sin theta. We already discussed. So I square RMS. So we are here that square is done on both the sides. So the negative become positive. 1 by 2 pi 0 to 2 pi I square d theta. But here only we have 1 by pi is enough, right, because it is a symmetrical value. So 1 by pi 0 to pi I square d theta. So 1 by pi 0 to pi I square is Im square into sin square theta d theta. This Im square sin square theta into d theta. Now we consider only half cycle because it is symmetrical. The sin square theta, before integrating we need to change it. So the sin square theta is written as 1 minus cos 2 theta divided by 2 into dt. This Im square is taken outside because of constant. So Im square divided by pi integral 0 to pi 1 minus cos 2 theta divided by 2. Sin square theta is now changed into 1 minus cos 2 theta divided by 2. Now we can easily integrate this. This 2 also taken outside. So Im square divided by 2 pi into the integral 0 to pi 1 minus cos 2 theta into d theta. Now we need to integrate this. We'll go refer here. I RMS square equal to Im square divided by 2. So the integral 1 is, that is d theta. Integral d theta is theta. Integral cos 2 theta is sin 2 theta divided by 2. Right? These two terms are integrated. Now we'll substitute the limit. First substitute the upper limit pi. So theta is pi minus sin 2 pi divided by 2. Then substitute the lower limit. At the time negative will be there, minus 0. Here already negative is there, so that become positive, sin 0 by 2. So pi minus sin 2 pi by 2 minus 0 plus sin 0 by 2. So the sin pi is 0, sin 0 also 0. Only we have pi. So Im square divided by 2 pi, pi minus 0. That is Im square divided by 2, only pi is available. This pi got cancelled. Right. So what we have, this Im square divided by 2. Im square divided by 2. Now we'll take the square root on both the sides. So that I RMS equal to Im divided by root 2. This Im square become Im, 2 become root 2. So the 1 divided by root is nothing but 0.707 Im. Right. The numerical value available. So I RMS equal to 0.707 times of Im. Now we'll go to the next parameter. So the next is the form factor. There are two factors available, form factor and peak factor. Form factor, what is form factor? It is the ratio of RMS value to average value of an alternating quantity. So this is one reference. What is the ratio between RMS value and average value? It is the ratio of RMS value to average value. For sine wave, we already calculated what is the RMS value and average value. Just now we got the derivation. What is the RMS value and average value? Now we'll substitute. For sinusoidal waveform, form factor equal to RMS value by average value. Now we calculated RMS value is Im by root 2. Average value is 2 Im by pi. Right. So that it is Im by root 2. While going to numerator, it become pi divided by 2 Im. So this Im got cancelled. What we have? Pi divided by 2 root 2. So by simplifying this, which is nothing but 1.11. So for a sinusoidal waveform, the form factor is 1.11. So these two values we already calculated, that is substituted. After simplification we got. So form factor of a sinusoidal waveform is 1.11. Then we'll go to the peak factor. One more factor is available. It's called a peak factor. So it is a ratio of peak or maximum value to the RMS value of an alternating quantity. So it is a ratio between peak value to RMS value. For again we will find the for sine wave. For sine wave, the peak value is Im. The RMS value we already calculated, Im by root 2. So while going to numerator, what will happen? Im into root 2 by pi. This Im by root 2 become root 2 by Im while going to numerator. So Im got cancelled. Only we have root 2. So the root 2 value is 1.41. So the form factor, so this is not a form factor, it's peak factor. It is a peak factor for a sinusoidal waveform is 1.41. The form factor is 1.11. The peak factor is 1.41. So in this video we discuss about the AC terminology, starting from waveform, cycle, time period, everything. Then we discuss the average value, RMS value. Then two different factors, form factor and peak factor. Thank you. Welcome viewers. In this video we will see the RMS value and average value of half wave rectifier as well as full wave rectifier. First we will consider the half wave rectifier. We will see the expression for RMS value, or also it is called as effective value. In half wave rectifier, during positive off cycle the diode is forward bias, so we will get the positive voltage. During negative off cycle the diode is reverse bias, so there is no voltage is available. So voltage available only during positive off cycle. The same thing repeated. So the waveform available between 0 to pi. From pi to 2 pi the current or voltage is 0. Here we consider the current. So I equal to Im sin theta, the general formula that is applicable for 0 to pi. 0 to pi the voltage available. In case of pi to 2 pi the current is 0. So based on that we will go for the derivation. RMS value equal to I RMS square equal to 1 divided by 2 pi integral 0 to 2 pi I square d theta. So this is the base period, full cycle, we have considered full cycle. So that 1 divided by 2 pi, limit also 0 to 2 pi. But here the current available only 0 to pi, so we can change it as 0 to pi. From pi to 2 pi the current is not available, as there is no waveform from pi to 2 pi, so the limit is changed from 0 to pi. Now we will substitute this I square, this I value is nothing but Im sin theta. So that 1 divided by 2 pi 0 to pi Im square sin square theta into d theta. This Im square is taken outside, so Im square divided by 2 pi. This sin square theta is written as, in order to go for the integration, the sin square theta is converted into 1 minus cos 2 theta divided by 2 into d theta. These 2 also we can take outside. So Im square by 4 pi theta. Now we will go for the integration. This integral 1 is nothing but d theta. So integral d theta is theta. Integral cos 2 theta is sin 2 theta divided by 2. Now we'll substitute the limit 0 to pi. So Im square divided by 4 pi, substitute the upper limit pi. So pi minus, here also sin 2 pi by 2, substitute the lower limit is 0. Here already negative is there, so that become positive, sin 0. So in this sin 2 theta also 0, sin 0 also 0, only we have pi. So Im square divided by 4 pi into pi. So this pi got cancelled. So what we have, Im square divided by 4, that is I RMS square equal to Im square divided by 4. Now we'll take square root on both the side. So I RMS equal to Im by 2. The square root of Im square is Im, square root of 4 is 2. So this 1 by 2 is 0.5. So 0.5 Im. So half wave rectifier, the RMS value of current is 0.5 times of maximum value, 0.5 Im. Now we got the expression for IRMS for half wave rectifier. Now we'll go to the average value. Now we'll see the average value of half wave rectifier. What is the formula? I average equal to 1 divided by 2 pi 0 to 2 pi I into d theta. Same thing, but here square is not there. Previously we have RMS square. Now we have average value. So 1 divided by 2 pi will split into 2, 0 to pi and pi to 2 pi. I d theta and I d theta. So 1 divided by 2 pi, 0 to pi, I is nothing but Im sin theta into d theta. From pi to 2 pi the current is not available, so it becomes 0. So we'll take this Im outside. So Im by 2 pi, the integral sin theta is minus cos theta. We need to substitute the limit 0 to pi. So while substituting, what will happen? Im by 2 pi, first to substitute the upper limit, minus cos pi plus cos theta. While substituting lower limit, negative is there, already one negative is there, so it becomes positive. Now we'll substitute the value. So Im by 2 pi, cos pi value is minus 1, already one minus is there, cos 0 value is 1. So Im by 2 pi, this become positive, minus of minus 1 become positive, plus 1, 1 plus 1, 2. So this 2 got cancelled, we have Im by pi. So 1 divided by pi is 0.318 Im. So the average value of the half wave rectifier is 0.31 times of Im. Now we got the average value as well as RMS value of the half wave rectifier. From that we can find the form factor. We can easily find the form factor. For half wave rectifier, the RMS value what we calculated is 0.5 times of Im, that is maximum value. Average value equal to 0.318 times of maximum value. Just now we calculated 0.31 times. Now we'll find the form factor. Form factor equal to RMS value by average value. So average value, what is the RMS value? 0.5 times of maximum value. This is nothing but Im divided by average value, 0.31 times of maximum value. This maximum got cancelled. So 0.5 divided by 0.318, that is nothing but 1.57. So the form factor for the half wave rectifier is 1.57. Now we'll go to the full wave rectifier. Now we'll go to the full wave rectifier. First we'll see the RMS or effective value. So in the full wave rectifier, we know that there are 2 diodes or 4 diodes will be available. So during positive half cycle, the one set of diode is forward bias, so we'll get the positive voltage. During negative half cycle, another set of diode is forward bias, so that we'll get the current during negative half cycle also. So every half cycle will get the voltage in case of full wave rectifier. Both positive half cycle and negative half cycle is rectified, so that it is called a full wave rectifier. So for every half cycle we are getting the positive current from 0 to 2 pi, pi to 2 pi, everywhere. So I equal to Im sin theta. This is the formula. Now we'll go to the I RMS square equal to 1 by pi 0 to pi I square d theta. Why we are taking here pi? Previously we have 2 pi, because so every half cycle is symmetrical here. 0 to pi is symmetrical with pi to 2 pi, 2 pi, pi to 3 pi. Every half cycle is symmetrical. So we need to consider only one half cycle is enough. Next half cycle is similar to the first one. But in case of half wave rectifier, 0 to pi the voltage available, pi to 2 pi the voltage is not available. So we taken full cycle. Here only half cycle is enough, because the waveform is symmetrical in every half cycle. Now we substitute the limit 1 by pi 0 to pi, substitute this value Im square sin square theta. This Im sin theta, so while square it become Im square sin square theta. In order to integrate, we need to change the sin square theta as a 1 minus cos 2 theta divided by 2. This Im square is taken outside. So Im square by pi. I will go for the integration. Im square by 2 pi. This 1 is the integral 1 is theta. Cos 2 theta is sin 2 theta divided by 2. This 2 is taken outside. So that Im square divided by 2 pi. Only we have 1 minus cos 2 theta. 1 minus cos theta, while integrating it become theta minus sin 2 theta divided by 2. Now we will substitute the limit. Im square divided by 2 pi, substitute the upper limit pi. Pi minus sin 2 pi by 2, substitute the lower limit. At that time we will get negative, minus 0. Here already one negative is there, so it become positive. This will be positive, not a negative. Sin 2 0. So in this sin 2 pi also 0, sin 0 also 0. Only we have pi is available. So Im square divided by 2 pi into pi. So pi got cancelled. So what we have only Im square divided by 2. That is I RMS square equal to Im square divided by 2. Now take the square root on both the sides. So that I RMS equal to Im divided by root 2. The square root of I RMS square is I RMS, Im square is Im, square root of 2 is this, square root of 2. So while simplifying this 1 by root 2, while simplifying what we got, 0.707 Im. So the RMS value of current for full wave rectifier is 0.707 Im. Now we'll go to the average value. So for the average value, the formula is 1 divided by pi 0 to pi I d theta. Because of symmetrical, we consider only pi. Now substitute the value 1 divided by pi 0 to pi. I is nothing but Im sin theta into d theta. You take the Im outside because constant, Im by pi. Integral sin theta is minus cos theta. Now substitute the limit Im by pi. Substitute the upper limit, already one minus is there, minus cos pi. While substituting lower limit, one minus will be there, already one minus there, so it become plus. Minus cos pi plus cos 0. So Im by pi minus, this cos pi is minus 1, plus cos 0 is plus 1. So Im by pi minus of minus 1 become plus 1. So 1 plus 1, 2. 2 Im by pi. By simplifying this, 2 by pi is 0.637 Im. I average equal to 0.637 times of Im. Now we got the average value as well as RMS value. From this we can find the form factor. So the form factor for full wave rectifier, the form factor formula is RMS value by average value. Both are we calculated. Average value, RMS value is 0.707 times of maximum value, that is Im. Average value is 0.63 times of maximum value. Just now we calculated. So this maximum value got cancelled. 0.707 divided by 0.637 is nothing but 1.11. So the form factor for the half wave full wave rectifier is 1.11. Now we'll go to the peak factor. One more factor is available, peak factor. We'll see for half wave as well as full wave rectifier. So the peak factor is nothing but maximum value by RMS value. So for half wave rectifier, peak factor equal to maximum value divided by the peak RMS value is 0.5 into maximum value. Already we calculated. So maximum value got cancelled. 1 divided by 0.5 is nothing but 2. So for peak factor of half wave rectifier is 2. Similarly, full wave rectifier, maximum value divided by RMS value. RMS value is 0.707 into maximum value. Got cancelled. So 1 divided by 0.707 is nothing but 1.414. So now we calculated peak value also. For half wave rectifier it is 2. For full wave rectifier it is 1.414. Now we will go for the comparison. Comparison table is available. So this is a half wave rectifier, this is a full wave rectifier. What is the average value of half wave rectifier? Im by pi. Full wave rectifier 2 Im by pi. For RMS value, half wave rectifier is Im by 2, full wave rectifier Im by root 2. The form factor half wave rectifier is 1.57. For full wave rectifier 1.11. The peak factor for half wave rectifier is 2, full wave rectifier is 1.414. So in this video we got the expression for RMS value and average value of half wave rectifier as well as full wave rectifier, and also we calculated the form factor and peak factor. Thank you. Welcome viewers. In this video we will see the AC through the resistance only. When the AC current is flowing through the resistor, what is the behavior of the voltage, current, what is the average power, what is the instantaneous power, This thing we will discuss in this video. Now consider the alternating quantity is applied to the resistive circuit as shown in the diagram. So the resistor is available, the alternating current, the alternating quantity, that is alternating voltage, AC voltage is applied to the resistor, Vt. This It is the current flowing through the resistor. Because of alternating quantity, it is Vt It. Because the current or voltage changes with the given time. In this resistor, so this is the applied voltage, Vm, the sign voltage. So positive cycle and negative cycle. Now we'll see this current waveform. This is a current waveform. In case of resistor, both current and voltage are in phase. In phase means current and voltage starts at 0 degree itself. There is no leading or lagging. Due to the magnitude, it slightly reduces, but current also in phase with the voltage. This is the amplitude of voltage, Vm. This is the amplitude of current, Im. So this is nothing but V of t, waveform of the applied voltage. This is I of t, waveform of the current. Now we'll analyze how this current and voltage are in phase with the, both are in phase in case of resistive circuit. In terms of equation, we will analyze. The resistive circuit, both current and voltage are in phase. We will analyze in terms of the equation. Now V of t equal to Vm sin omega t. That is, we will take it as equation 1. This is the applied voltage. The voltage applied to the circuit is Vm sin omega t. We will take this equation number 1. By using the Ohm's law, V of t equal to R into I of t. V equal to IR. That is a Ohm's law given. So V of t equal to R into I of t. Both are in terms of time period. Now we'll substitute this V of t from this equation, Vm sin omega t. This V of t is replaced by this Vm sin omega t. That is equal to R into I of t. Bring this R in the denominator. Vm by R sin omega t equal to I of t. What is Vm by R? V by R is nothing but current. No, it's rewritten like this. I of t equal to Vm by R into sin omega t. This term is written in left hand side. This term is written in right hand side. It is rewrite. So this Vm by R is nothing but Im. Voltage by resistance. V by R is nothing but Im. So I of t equal to Im sin omega t. So that is given. Vm by R is nothing but the maximum value of current Im. This R is the resistance of the circuit. I of t is instantaneous current passing through the circuit. Instantaneous current means at given instant. Now we can refer this equation 1 and 2. Equation 1, V of t equal to Vm sin omega t. I of t equal to Im sin omega t. So the angle is omega t. Both angles are same. So that means that this current and voltage are in phase with each other. So that is given. Comparing equation 1 and 2, we find that the alternating voltage and current are in phase with each other. That only we already referred in the waveform. So by analyzing these two equations, we come to know that both are in phase. Now we'll find the instantaneous power. Now we'll go for the instantaneous power of the R circuit. So the instantaneous power means at given instant. Average power means by considering the entire cycle. P equal to V of t into I of t. Power equal to voltage into time. The voltage into current. The formula is available. So V of t is Vm sin omega t. I of t is Im sin omega t. So it is Vm into Im sin square omega t. So the sin square omega t can be written as 1 minus cos 2 omega 2 divided by 2. So we got Vm Im into 1 minus cos 2 omega 2 divided by 2. We'll go for further simplification. So the 2 is taken outside. So P equal to Vm Im divided by 2 into 1 minus cos 2 omega t. Now multiply the term inside. So Vm Im divided by 2 minus Vm Im divided by 2 into cos 2 omega t. This term is multiplied inside. So from that you can easily see that this is the DC term. There is no cos or sine is available. So this is the AC term or harmonic part. The DC part and AC part. Now we'll go to the average power. The derivation for average power. So the average power equal to 1 divided by T, 0 to T, P into dt. So the average power means we need to integrate for a given time. Then we will get the total average power. Normally average means we'll take I1 plus I2 plus I3 divided by N. Like that we are going for integration. By integrating the entire cycle we will get the average. So 1 by P, 1 by pi, 0 to pi, P into dt. Now the power we already calculated. So 1 by pi, 0 to pi, Vm Im divided by 2 minus Vm Im divided by 2 cos 2 omega 2 into dt. The instantaneous power what we calculated earlier. Now this Vm Im by 2 is available in both the terms. So we'll take it as outside. So Vm Im divided by 2, already 1 pi is there. So Vm Im divided by 2 pi. So here we have 1 minus cos 2 omega t into d omega t. Now we'll go for the integration. So Vm Im divided by 2 pi, the integral 1, that is d omega t is omega t minus cos 2 omega t. Integral cos 2 omega t is sin 2 omega t divided by 2. Now substitute the limit, the pi minus sin 2 pi divided by 2. The lower limit is 0. So sin 0 also 0, this also 0. So they are not substituted. So the sin 2 pi also 0. So only we have pi. Vm Im divided by 2 pi into pi. This pi got cancelled. So we have Vm Im divided by 2. So in this lower, only upper limit substituted, lower limit is 0. So this value becomes 0, sin 0 also 0, so that not written. Only the upper limit is substituted. Again in the upper limit, this value also 0, sin 2 pi is 0. Now Vm Im divided by 2 pi can be written as Vm by root 2 into Im by root 2. This 2 is written is root 2 into root 2. Root 2 into root 2 is nothing but 2. So what is Vm by root 2? That is RMS value. Im by root 2 is also RMS value, current and voltage. Vm by root 2 is Vrms. Im by root 2 is IRMS. Now we got the expression for average power. So in this video we analyze the when the AC current is flowing through the resistor, what is the behavior of current and voltage. From the equation we analyze that both current and voltage are in phase with each other. And also we got the expression for instantaneous power and average power. Thank you. Welcome viewers. In this video we will see the AC through the inductor only. When the alternating current is flowing through the inductor, what is the behavior of the voltage, current, and what is the expression for average power and instantaneous power. These things we'll see in this video. Now consider an alternating quantity is applied to a pure inductive as shown in the diagram. So the inductor is available, in that the alternating voltage is applied. Vt. V of t is the alternating voltage. I of t is the alternating current flowing through the inductor. The pure inductor refers normally the inductor having some internal resistance. Pure inductor means only inductance will be there. There is no resistance. We are not considering the internal resistor of the inductor. Only we consider this inductor value only. That is called a pure inductor. So in case of the inductor, we will see the what is the voltage, applied voltage. This is the AC voltage applied to the inductor, V of t. The maximum value is, amplitude is Vm. It starts at 0 degree. The inductor, normally the current lagging the voltage by 90 degree. So this is the current waveform. Current starts only at pi by 2, 90 degree. There is a phase difference of 90 degree between voltage and current. So this is the current waveform. It starts only at 90 degree. The dotted line indicates the waveform of the current. So there is a phase difference of 90 degree. So this is Im. Now we'll see how the current is lagging. What is the proof for that? By equation, by analyzing the equation, we will see what is the how the current is lagged by voltage by 90 degree. By using the equation, we will analyze. As per the Faraday's law of electromagnetic induction, an EMF is induced in the coil when the alternating voltage is given to the inductor, and due to rate of change of flux, EMF is induced in the coil. This EMF is equal to magnitude and opposite polarity of the applied voltage. So both are opposing together. That is based on the Faraday's law of electromagnetic induction. So this EMF is given by V of t equal to L di by dt. The induced EMF is proportional to the rate of change of current and also proportional to the rate of change of flux. Right? Here we consider the current. V of t equal to L di by dt. But V of t equal to Vm sin omega t. This is applied voltage. V of t equal to Vm sin omega t. You take this equation number 1. This is a voltage equation. Now we'll substitute this Vm sin omega t in the above equation. So that Vm sin omega t equal to L di by dt. Now bring this L in the denominator in the left hand side. So Vm by L sin omega t, and bring this dt also in the numerator left hand side. So Vm by L sin omega t into dt equal to di. So we'll rewrite this di equal to Vm by L sin omega t into dt. So by integrating on both the side, we'll get the total current. So integrate on the both the side. Integral di equal to integral Vm by L sin omega t into dt. So this integral di is nothing but I of t. Vm by L is constant. The sin omega t, integral sin omega t is minus cos omega t divided by omega. Now we'll go for further simplification. So I of t equal to Vm by omega L minus cos omega t. So Vm by omega L minus cos omega t can be written as sin omega t minus pi by 2. Both are equal. Cos omega t is equal to sin omega t minus pi by 2. So I of t equal to Vm divided by XL. This omega L, omega into L can be written as XL. XL is nothing but omega into L, inductive reactance. That is very similar to resistance. In the inductive circuit, the resistance offered by the inductor is nothing but inductive reactance. It is very similar to the resistance. So V by resistance, inductive reactance, V by inductive reactance can be written as current. I equal to V by R. So here V by XL. So this Vm by XL is replaced by Im. Sin omega t minus pi by 2. So we'll take this equation number 2, second equation, that is current. What is the first equation? V of t equal to Vm sin omega t is the first equation. So after simplification, we got the equation for current, that is equation 2. This is the applied voltage, equation 1. So by comparing these two, what is the difference? There is a pi by 2, minus pi by 2 is available. That is current is lagging the voltage by minus pi by 2. Here only omega t is available. Here omega t minus pi by 2 is available. So that indicates when comparing the equation 1 and 2, we come to know that there is a phase difference of pi by 2 between voltage and current. That is, it shows that current lags behind the applied voltage by pi by 2 or 90 degree. This minus pi by 2 refers lagging. Current is lagging by voltage. In other words, the voltage leads the current by 90 degree. Right? So by analyzing the two equations, we come to know that current is lagging the voltage by 90 degree. Now we'll go for the instantaneous power. What is instantaneous power at a given instant? It's called a given instant. P equal to V of t into I of t. So V of t is the applied voltage, Vm sin omega t. I of t we already calculated. Im sin omega t minus pi by 2. So this is nothing but equation 2. This is equation 1. So Vm sin omega t into Im. So sin omega t minus pi by 2 can be written as minus cos omega t. We already discussed that. This only replaced to sin omega t. Now again we come to original form. So the negative sign is available. So minus Vm Im sin omega t into cos omega t. So the sin 2 omega t equal to 2 sin omega t cos omega t. So sin 2 omega t divided by 2 equal to sin omega t into cos omega t. So this sin omega t into cos omega t can be replaced by sin 2 omega t divided by 2. So that is written here, sin 2 omega t divided by 2. So finally what we got, p equal to minus Vm Im divided by 2 sin 2 omega t. So this value is replaced by sin 2 omega t divided by 2 based on this formula. Now we got the expression for instantaneous power. Now we'll go for the average power. Average power equal to 1 divided by t 0 to t p into dt. So time period, base time. So 1 by pi, we will take pi, half cycle. 1 by pi equal to 0 to pi minus Vm Im divided by 2 sin 2 omega t into dt. This p is available here. So instantaneous power, that is substituted. Now we'll go for the further simplification. So minus Vm Im divided by 2 integral sin 2 omega t is minus cos 2 omega t divided by 2. So already one minus is there, here also one minus is there. So minus Vm Im divided by 2 pi, substitute the limit. The negative is as it is, minus cos 2 pi divided by 2 minus this lower limit. While substituting lower limit, it becomes plus cos 0 divided by 2. So this cos 2 pi now, cos 2 pi plus so cos 2 pi value is 1. So already one minus is there, minus 1. Cos pi value is 1. So minus 1 plus 1, it become 0. The average power is become 0. Due to this 0 term, the entire average power become 0. So in this video, we discuss about when the alternating current is flowing through the inductor, what is the behavior of voltage and current. We identify that current is lagging the voltage by 90 degree. And also we got the expression for instantaneous power and average power. Thank you. Welcome viewers. In this video, we'll see the AC through a capacitance only. When the AC voltage is applied to the capacitance, what is the behavior of the circuit? What is the behavior of voltage, current, and what is the expression for instantaneous power and average power? We will see in this video. Now consider the capacitor is given with the AC voltage V of t equal to Vm sin omega t. The alternating voltage is applied to the capacitor. This I of t is the instantaneous current flowing through the capacitor. I will refer the waveform. This is the supply voltage V of t. V of t is applied. It starts at 0 degree. The maximum value is Vm. Is referred by V of t. V of t equal to Vm sin omega t. In capacitor, the current is leading by 90 degree. Current will start before the starting of voltage. Before starting the voltage, current starts 90 degree. Before that, it means the current is leading the voltage by 90 degree. So current start from here. Before starting the voltage, the current started at an angle of 90 degree. So this is the current waveform I of t. This is the maximum value Im. So the current is leading the supply voltage by 90 degree in the capacitor hole. And the capacitor. Now we'll see that how it is. We'll see through the equation. By analyzing the voltage and current equation, we will analyze what is how it is, how the capacitor current is leading by voltage by 90 degree. We will see the equation so that we will come to know how this leading is happen. Now consider the supply voltage. The applied alternating voltage V equal to Vm sin omega t. So this is the supply voltage. We take this equation number 1. The instantaneous value of current in the circuit at the time t is given by I equal to dq by dt. Because of capacitor is connected, the I equal to dq divided by dt, rate of change of charge. But we know that q equal to cv. We can replace q equal to cv, right? So I equal to d by dt of q is replaced by cv. Now c is taken outside, so I equal to c dv by dt. Now I equal to c into d by dt of this v is replaced by the first equation, Vm sin omega t. The v is substituted as Vm sin omega t. So I equal to c, this Vm is constant, so we taken outside. So differentiation of sin omega t is cos omega t into omega. So that I equal to omega into c into Vm, omega c Vm into cos omega t. So this omega c is brought to the denominator. So 1 divided by omega c. So omega c, 1 divided by omega c, both are equal. So this 1 divided by omega c is nothing but Xc. That is a capacitive reactance, which is very similar to the resistance, opposing the flow of current. Is very equal to the resistor value. So 1 divided by omega c is replaced by Xc. Now I equal to Vm by Xc into cos omega t. Xc is nothing but capacitive reactance, that is 1 divided by omega c. Now Vm by Xc can be written as Im. I equal to V by R. Here V by Xc. Voltage by capacitive reactance is equal to current. Very similar to I equal to V by R. So I equal to Im cos omega t. So this cos omega t can be written as sin omega t plus pi by 2. In order to compare equation 1 and 2, the cos is now changed into sin omega t plus pi by 2. That is I equal to Im sin omega t plus pi by 2. So that is I equal to Im sin omega t plus pi by 2. We'll take it as equation number 2. Now we got the equation for current. What is the first equation? V of t equal to Vm sin omega t. This is the equation 1. So applied voltage. Now compare these two equations, equation 1 and 2. What is the sin value? Here sin omega t, here sin omega t plus pi by 2. That is current is leading the voltage by 90 degree, pi by 2 degree. In case of inductor it is minus pi by 2. Minus pi by 2 means lagging the voltage by 90 degree. Here plus pi by 2 is there. So by comparing equation 1 and 2, there is a phase difference of pi by 2 or 90 degree between voltage and current. So that it shows that the current is lead the applied voltage by pi by 2 or 90 degree. So that is the waveform we already discussed. The current starts before the voltage starts by 90 degree. So now by equation we are clearly identified that current is leading the voltage by 90 degree. Now we'll go for the instantaneous power. Instantaneous power means at a given time. P equal to V of t into I of t. V of t is Vm sin omega t. This is equation 1. I of t is Im sin omega t plus pi by 2. This is equation number 2. So Vm into Im sin omega t. This sin omega t plus pi by 2 can be written as cos omega t. So this sin omega t into cos omega t can be written as cos 2 omega t divided by 2 based on this formula. Cos 2 omega t equal to 2 into sin omega t cos omega t. Bring these 2 in the denominator. So cos 2 omega t divided by 2 is equal to sin omega t into cos omega t. So this sin omega t into cos omega t is replaced by this parameter cos 2 omega t divided by 2. So by rewriting P equal to Vm Im divided by 2 cos 2 omega t. So this is the instantaneous power. From this we can find the average power. we can calculate the average power. Average power equal to, average mean we need to integrate for a entire time period, so that we'll get average. 1 divided by t, 0 to t, p into dt. What is the time period? Pi, half cycle. 1 divided by pi, 0 to pi. Then the instantaneous power is available here. Vm Im by 2 cos 2 omega t into dt. So Vm Im by 2 is taken outside, so that Vm Im divided by 2 pi. Cos 2 omega t is sin 2 omega t divided by 2. Integral sin cos 2 omega t is sin 2 omega t divided by 2 with the limit 0 to pi. Now we'll substitute the limit, so that Vm Im divided by 2 pi, we substitute this limit sin 2 pi divided by 2, by substitute the lower limit, so minus sin 0 by 2. So the sin 2 pi value is 0, sin 0 also 0, so totally the power is 0. The average power in the capacitive circuit while applying AC voltage is 0. So in this video we discuss about what is the behavior of current and voltage when AC voltage is applied to the capacitor. We identify that current is leading by 90 degree. We analyze the two equation. From current and voltage equation, we identify that current is lead by 90 degree. Also we calculated the expression for instantaneous power and average power. Thank you. Welcome viewers. In this video, we'll see the performance of the RL series circuit. When the resistance, pure resistance and pure inductance is connected in series, is called the RL series circuit, energized by the AC supply voltage. We are going to analyze the performance of this circuit, RL circuit. What is the voltage equation for voltage, current, phase angle between voltage and current, power triangle, impedance triangle, power factor. These things we are going to analyze in this RL series circuit. So in this RL series circuit, this R and L is connected in series, energized by the AC supply voltage. It's a current I. Because of series circuit, the same current is flowing through R as well as L. The current flowing through the R and L is same current is flowing. Now we'll consider this V equal to Vm sin omega t, applied voltage. So I is the effective value at any instant. Small I is the circuit current at any instant. Vr is the potential difference across the resistor R. VL is the potential difference across the inductor L. F is the frequency of the applied voltage. Right? Now we'll go to the analysis. The same current I is flowing through the resistor as well as inductor, so we can take current as a reference vector. Current is taken as reference vector. So based on that, the voltage across the resistor VR equal to I into R, V equal to IR. That is in phase with the current, because in the resistor always the current and voltage are in phase. Similarly, the voltage across the inductor VL equal to I into XL. XL is nothing but the reactance, inductive reactance. For inductor always the leading the current by 90 degree. That is, current is lagging. It means the voltage is leading the current by 90 degree. The resistor always voltage and current are in phase. But in case of inductor, the current is lagging. In other words, the voltage is leading the current by 90 degree. So based on that, we have the phasor diagram is available. So this is the reference vector, current vector. The voltage across the resistor R, VR equal to I into R, that is in phase with the current, so that it is drawn in the horizontal. Then VL, voltage across the inductor I into XL, that is 90 degree leading, right? So that it is drawn in a vertical line, 90 degree leading. This indicates 90 degree leading. So this is the voltage drop across resistor in phase with the current. Voltage drop across the inductor 90 degree leading with the current. So sum of these two, vector sum of these two is nothing but the total voltage V. That is I into Z. Z is nothing but impedance. Impedance is nothing but the sum of resistor and inductance, capacitive reactance. So this is the voltage across resistor, so voltage across inductor, So sum of these two is the total voltage V, that is I into Z, that is Z is nothing but the impedance. So from this diagram, phasor diagram, we can go for the further analysis. So the total voltage V equal to VR plus VL, voltage drop across resistor and inductor. So V equal to I into R plus J I into XL. What is this J? The J represents the voltage is leading the current by 90 degree. The J represents the 90 degree. The J operator that indicates the leading by 90 degree. So we can take I outside, so that R plus JXL, bring the I in the denominator. So V by I equal to R plus JXL. So this V by I is nothing but the impedance, V by I. So V by I is the normally the resistance R. Here we have resistance as well as inductive reactance. So combinedly where it is termed as the impedance. So impedance equal to R plus JXL. So for this circuit, the impedance is R plus JXL, right? So that is nothing but V by I is taken as a impedance. Then the magnitude of the impedance, Z equal to modulus of Z equal to square root of R square plus XL square. So this is nothing but here the impedance, the magnitude of the impedance. Now this is nothing but here there are two forms available, rectangular form and the polar form. We'll see that. For that we need an angle. So from this diagram, from this phasor diagram, we can calculate the tan pi. Tan pi equal to opposite side by adjacent side. IXL divided by IR. So II got cancelled, XL by R. So pi equal to tan inverse XL by R. The angle between the voltage drop across resistor and inductor is nothing but tan inverse XL by R. Now we can represent the impedance in two different forms. Z equal to R plus JXL is a rectangular form. Z equal to magnitude of Z and angle pi. This is the polar form. So we can represent the impedance in two different forms, rectangular form and polar form. This Z can be calculated from this formula, pi can be calculated from this formula. Now we'll go for the phase angle between the current and voltage. Now we'll see as per the property of the series circuit, the voltage can be written as V of t equal to VR of t plus VL of t. That is total voltage equal to voltage drop across resistor plus voltage drop across inductor. Right? This is another format. In order to analyze the phase angle between current and voltage, again we are analyzing this voltage. So VR is nothing but R into I of t, V equal to IR. Similarly, the voltage across the inductor is L di by dt. Now we know that I of t is nothing but Im sin omega t. That is for a resistive circuit in phase with the voltage. So I of t equal to Im sin omega t. So di by d of t, differentiate on both the side. Im sin omega t, differentiation of sin omega t is cos omega t into omega. So that is omega Im cos omega t, di by dt. That is equal to omega Im sin omega t plus pi by 2. This cos omega to omega t can be written as sin omega t plus pi by 2. Now we got the expression for this di of t divided by dt as well as I of t is available. Now we can substitute these two values in the equation 1. This I of t and di of t can be replaced with this expression. So substitute I of t and di of t in the equation 1, so that V of t equal to Rim sin omega t plus L omega Im sin omega t plus pi by 2. So that is can be written as Rim sin omega t. This omega into Im, omega into L is nothing but XL, inductive reactance. So Im into XL sin omega t plus pi by 2. Now we got the two terms, term 1 and term 2. Now we can analyze these two terms. So the first term is the represent the applied voltage and voltage across the resistor. This term refer the voltage across the resistor. See, the phase angle is omega t only. So the current value also omega t, the voltage also we got omega t, so it is in phase with each other. The voltage across the resistor is in phase with the current. But in case of the second term, voltage across the inductor, we have omega t plus pi by 2. The plus pi by 2 is available. So the second term in the above equation is compared with the equation 1. The phase difference of pi by 2 or 90 degrees available. There is a phase difference of pi by 2 or 90 degree between this voltage and current. So it is obtained by rotating VL vector 90 degree in the vector diagram. So due to that only we are getting the 90 degree. The voltage across resistor and voltage across inductor differ by 90 degrees. So that is indicated by this equation. So based on that we can draw the waveform. So this is the voltage. It starts at 0 degree. So the inductive circuit, the current is lagging or voltage is leading. So current starts after pi. Approximately if it is pi by 2 means it is pi by 2 degrees pi. After pi only the current starts. So there is a phase difference of pi between current and voltage, that is current is lagging the voltage. So based on that we can write the waveform V equal to Vm sin omega t. But I equal to Im sin omega t minus pi. This minus pi indicates the current starts after the voltage with an angle of pi. So that is indicated by omega t minus pi. Right? So we got the waveform. Current and voltage is clearly indicated. Current is lagging the voltage by an angle of pi. That is indicated in the equation. Now we'll go for the impedance. So we'll find the impedance for this RL circuit. The impedance is nothing but opposition of circuit to flow of alternating current. It is very similar to resistance. Here we have inductor is available. So inductance, inductive reactance and resistance combined is known as the impedance. So it is denoted by Z. So how it is represented by the triangle is a resistor. That is in phase with the current. 0 degree in phase with the current. This inductive reactance is 90 degree. There is a phase difference of 90 degree between the R and XL. So sum of these two, resistance and inductive drop, is nothing but a impedance. So impedance is the vector sum of resistance plus inductive reactance. So there is a 90 degree phase shift between the resistor and inductive reactance. So from this diagram we can find the value of sin pi. So this is the angle pi. Sin pi is nothing but opposite side by adjacent side. XL divided by Z. We cross multiply this so that XL equal to Z into sin pi. So we can find the XL by using this formula, Z sin pi. Then find the cos pi. Cos pi equal to adjacent side by hypotenuse. R divided by Z. Cross multiply this so that R equal to Z cos pi. So we can find the R value by using this expression. Similarly, XL value from this expression. Now we'll find the impedance. What is the expression for impedance? So impedance is R plus JXL, that we already discussed. R plus JXL is the impedance in a rectangular form. Then modulus Z angle pi is the polar form. How will you find this modulus of Z magnitude? That is square root of R square plus XL square. Then how will you find the angle pi? Tan inverse XL by R. Right? So the impedance can be represented in the two different form. One is rectangular form, another one polar form. In this polar form, this magnitude angle can be calculated from this formula. Now we'll go to the power triangle. So in the power triangle we have real power at the reference vector, real power. This reactive power, that is quadrature with the real power, that is 90 degree. The sum of real power and reactive power is the apparent power. This apparent power is nothing but vector sum of real power and reactive power. This real power is represented kilowatt. Reactive power represented kilo kVAR. The sum of these two is nothing but apparent power, that is represented kVA. Now we'll see what is real power, reactive power one by one. So this is the triangle, power triangle. So S equal to square root of P square plus Q square. This is the S. That is equal to S square equal to P square plus Q square. So S equal to square root of P square plus Q square. Another form we can represent, S is represented kVA, that is equal to square root of P is represented kilowatt, Q is represented kVAR. So kVA equal to square root of kilowatt square plus kVAR square. So this is a power triangle. Here 90 degrees between real power and reactive power. Now we'll see what is mean by apparent power, what is mean by real power, reactive power one by one. So the real power is nothing but the product of RMS value of voltage and current. Simply V into I. RMS value of voltage. V into I is nothing but a apparent power. The unit is kVA. What is real power? It is the product of applied voltage and active component of the circuit. There is two components available, active and reactive. So if you multiply the active component of current with voltage, that is called a real power or active power. That is nothing but, and another form, the power which is actually consumed or utilized in an AC circuit is called a active power. The given power is consumed or actually utilized by the circuit is called a AC, is called a real power. Another power is available, this is a reactive power. That will be dropped in the, that will be reacted in the circuit. That's why it is called a, the power that is consumed for energy conversion, consumed or utilized. So that is represented P equal to VI cos pi. The unit is kilowatt, right? So this is the active component that is actually consumed in the circuit. Then what about the reactive power? It is defined as the product of applied voltage and reactive component of the current. What is reactive component? Power which flow back or forth. That means it moves in the direction in the circuit, react upon itself, react. So some power is required to activate, that is called a reactive power. The power actually consumed is a active power. The power actually required to activate the circuit is called a reactive power. That's why it is called a reactive component or active component. So Q equal to VI sin pi. The unit is kVAR. So there are three power available, real power and reactive power. Sum of these two is nothing but a apparent power. Now we'll go to the power factor. So power factor is the ratio of real power to apparent power. Real power or true power. What is true power? Real power VI cos pi. What is apparent power? VI. So VI got cancelled. It is cos pi. So power factor is nothing but cos of angle pi. What is this pi? Is the angle between current and voltage. So power factor will give the cos of angle between current and voltage. For getting better result, the angle between current and voltage should be 0. So if it is 0 means the power factor will be 1. Right? So power factor is nothing but cos of angle between current and voltage. It is also defined in another form. Cos pi can be also calculated from the triangle, from the impedance triangle, R divided by Z. Right? It is also called as R divided by Z. So power factor is nothing but cos pi. That is nothing but pi is the angle between supply voltage and current. So in this video we discuss about RL series circuit. Resistor and inductor is connected in series. What is the behavior of the circuit with respect to voltage, current, phase angle, impedance, power factor, power triangle and other related terms. Thank you. Welcome viewers. In this video we will see the RL series circuit, that is resistor and capacitor is connected in series. Consider this diagram. Resistor and capacitor is connected in series and energized by the AC voltage. We will see what is the behavior of this circuit. What is the current, voltage, what is the impedance, power factor, power we are going to analyze. So here resistor or capacitor are connected in series, energized by the AC voltage. So the VR is the voltage across the resistor. Vc is the voltage across the capacitor. So the description is given here. V equal to Vm sin omega t, that is the applied voltage. I is the current of circuit current at any instant. The capital I is the effective value of current. Vr is the potential across resistor R. Vc is the potential drop across capacitor. F is the frequency. Now in this series circuit, the same current I is flowing through the resistor as well as capacitor. So the current is taken as a reference vector. Now we are going to draw the vector diagram. In that we are taking current as a reference vector because the same current is flowing through capacitor as well as resistor. So based on that, this voltage across the resistor VR equal to IR in phase with the current. So the voltage across the resistor is I into R. So the resistor we know very well, it is always in phase with the current. The voltage across the capacitor VC equal to I into XC. This XC is nothing but capacitive reactance. So the capacitor always the current is leading, that is, otherwise the voltage is lagging the current by 90 degree. Current is leading in capacitive circuit, and other words the voltage is lagging the current by 90 degree. So the voltage is now lagging the current. So based on that we have vector diagram is available, phasor diagram is available. So this is the voltage drop across the resistor, VR equal to IR. This is a voltage drop across the capacitor. So that is lagging the current. The capacitor across the voltage is lagging the current, so it is drawn downwards. So it is lagging the applied voltage, lagging the current. Vc equal to I into Xc. So sum of these two is the total potential. V is I into Z. The Z is nothing but impedance of the circuit. The vector sum of resistance and capacitive reactance is nothing but a impedance. So here voltage is lagging the current, so it is given in the downward direction. In case of RL circuit, the voltage is leading the current, that is current is lagging, voltage is leading. So in that case the inductive reactance will be drawn in upward direction. So leading, now it is lagging, voltage is lagging. So based on that we will go for the total voltage. V equal to VR plus Vc, that is IR minus JIXC. So this minus sign indicates it is lagging the voltage. If it is plus J means leading the voltage, leading the current. So the minus J represents lagging the current, that's why it is given minus. So take I outside, so that R minus JXC. Bring the I in the denominator, so V divided by I equal to R minus JXC. So V divided by I is nothing but impedance, that is equal to R minus JXC. So in the magnitude we will taking modulus, it is nothing but square root of R square plus XC square. So this is nothing but a impedance. So impedance of this RC series circuit is square root of R square plus XC square. So this is a rectangular form. We can write in a polar form also, another form is available. So from this phasor diagram, we can find the value tan pi. Tan pi is nothing but adjacent side by hypotenuse. IXC divided by IR. IXC divided by IR. I get cancelled, so XC divided by R. So from that pi equal to tan inverse XC by R. So the angle, the phase angle pi is nothing but tan inverse XC by R. While writing polar form, we can use this angle pi. Right? Now this is the rectangular form. Polar form, we can use this angle. Now we'll go to the phase difference between current and voltage. So because of series circuit, the applied voltage can be written as voltage drop across resistor plus voltage drop across capacitor. This is one more analysis in order to get the angle between applied voltage and current. So VR is nothing but R into I of t. V equal to IR. So R into I of t. The voltage drop across the capacitor is 1 by C integral I dt. So formula is available. What is I of t? I of t is nothing but Im sin omega t. So r into Im sin omega t plus 1 by c integral I of t is Im sin omega t into dt. So that is r into Im sin omega t plus this Im is taken outside, Im by divided by c. The integral sin omega t is minus cos omega t divided by omega. So that what will happen here, r Im sin omega t plus Im by omega c. This omega is taken outside, so omega into c minus cos omega t. So this minus cos omega t can be written as sin omega t minus pi by 2. Right? Minus of cos omega t can be written as sin of omega t minus pi by 2. Now we have two terms available. Now we can analyze these two terms so that we are able to find the angle between current and voltage. So the first term r Im sin omega t is the voltage drop across the resistor. That is in phase with the current. There is no angle here. Only omega t is available. That means voltage drop across the resistor is in phase with the current. The second term refers the voltage drop across the capacitor. See here minus pi by 2 is available. That is current is leading or voltage is lagging the current by 90 degree. So this voltage is lagging the current by 90 degree. That's why we got the in the phasor diagram the voltage drop across the capacitor is drawn downwards. So from this two term we are easily identify that voltage drop across the resistor in phase with the current, voltage drop across the capacitor is leading 90 degree or voltage is lagging the current by 90 degree. There is a phase difference of 90 degree. The current is leading or voltage is lagging. So based on that we can draw the waveform. See the voltage is starts at 0 degree. We know that current is leading. So before starting voltage the current start here itself. The current starts earlier. In case of inductor the current start later. Here the current start earlier. So there is a phase difference of pi between current and voltage. That is current is leading or voltage is lagging. Here current is leading. So based on that we can write V equal to Vm sin omega t. It starts at 0 degree. But I equal to Im sin omega t plus pi because it starts earlier. So it is added. If it is later minus pi. If it is earlier means in case of capacitor the current starts earlier. So sin omega t plus pi. So from that we can easily add the current I leads the applied voltage V by an angle of pi. There is a phase difference of pi, that is current is leading. Now we'll go to the impedance. So the impedance is nothing but the opposition of circuit flow of alternating current. It's like a resistance. Impedance is very similar to resistance. Here we have resistance as well as capacitive reactance combinedly known as impedance. That is nothing but opposing the flow of alternating current. It is denoted by Z. So the impedance triangle is available. This is the resistance R, that is in phase with the current. This is capacitive reactance Xc. That is the voltage is lagging the current, so that it's gone downwards. The voltage is lagging. That is current is leading but voltage is lagging. The sum of these two R and Xc is nothing but the impedance. So this is the phase angle between the R and Z pi. So from that based on that we can write the impedance Z equal to R minus jXc. This minus represent it is downwards lagging. Voltage is lagging. So that can be written as Z modulus of Z into pi, angle pi. It's a polar form. How will you find modulus of Z? Square root of R square plus Xc square. Then how will you find the pi, the angle, phase angle? So from this triangle we can find sin pi. Sin pi equal to opposite side by hypotenuse. Xc divided by R. Xc divided by Z. Opposite side by hypotenuse. Xc divided by Z. From that cross multiply this. So Xc equal to Z into sin pi. Similarly, find the value of cos pi. Adjacent side by hypotenuse. Adjacent side R by Z. So cross multiply this so that R equal to Z cos pi. Similarly, find the tan pi. Opposite side by adjacent side. Opposite side by adjacent side. Xc divided by R. So that pi equal to tan inverse Xc divided by R. So pi equal to minus tan inverse Xc by R because it is lagging. So from this the pi can be calculated from this value. So impedance given in rectangular form as well as polar form. This is a polar form. Now we'll go to the power triangle. Based on this we can analyze the power triangle. So the power triangle we have three different power available. It's a real power are called active power, actively utilized in the circuit. Its term is P, the unit is kilowatt. Another one reactive power, not consumed but it will react with the circuit. Some power required to initiate the circuit is called a reactive power. This term is Q, kVAR. Why it is downward? Because the voltage is lagging. Current is leading but the voltage is lagging, so that it is drawn downwards. The sum of these two, real power and reactive power, is the apparent power, total power, kVA. So S equal to square root of P square plus Q square. That is kVA equal to square root of kilowatt square plus kVAR square. Right? So the real power, reactive power and apparent power. Now we will see the definition. Apparent power is nothing but it is defined as the RMS value of voltage and current. S equal to V into I. The unit is kVA. Apparent power means RMS value of voltage and current. Now we'll go to the real power. It is defined as the product of applied voltage and active component of the circuit. Real power or active power means active component. What is active component? The power which is actually consumed or utilized in the circuit. For energy conversion, actually it is consumed. The power is actually consumed. Some of the power is not consumed. It is dropped in the circuit. That is called a reactive power. The power fully utilized for conversion is called a active power. So that is represented P equal to VI cos pi. The unit is kilowatt. Right? The power which is actually consumed or utilized is called a active power. Then what about the reactive power? It is the product of applied voltage and reactive component of the current. Reactive component. What is reactive component? The power which flows back or forth. That means it moves in both the direction in the circuit or react upon itself. The power is not converted. It is reacted. It is dropped in the circuit itself in order to initiate and other purpose. That is called a reactive power. So Q equal to VI sin pi. The unit is kVAR. Right? Now we discuss about the apparent power, real power and reactive power. Based on that we will go to the power factor. Power factor is a ratio of real power to apparent power. Real power or true power. What is true power? Real power VI cos pi. Apparent power VI. VI got cancelled. It is cos pi. So power factor is nothing but cos of angle between pi. The pi is nothing but the angle between current and voltage. So the power factor defines the cos of angle between current and voltage. So current and voltage, the angle between current and voltage is 0 means we'll get the better power factor 1. Cos 0, the angle is 0, cos 0 means 1. And another formula also available, the cos pi from the triangle, impedance triangle, we can find R divided by Z. Cos pi also calculated from the impedance triangle, that is R divided by Z. So pi is the angle between supply voltage and current. So in this video we discuss about the RC series circuit. Resistor and capacitor is connected in series. What is the behavior of the circuit? Thank you. Welcome viewers. In this video we will see the RLC series circuit. Consider this diagram. Resistor, inductor and capacitor are connected in series. It is energized by the supply AC voltage. Now we are going to analyze what is the behavior of the circuit. What is the voltage, phase angle between current and voltage, power factor, all these things we are going to analyze. So the V equal to Vm sin omega t is the applied voltage. I is the RMS value of the current. VR is the voltage across the resistor R. VL is the voltage across inductor. VC voltage across the capacitor. So the current I, same current I is flowing through all three elements, resistor, inductor and capacitor. So we can take current as a reference vector. So based on that, the VR, voltage drop across resistor, equal to I into R. Voltage drop across inductor is I into XL. Voltage drop across capacitor is I into XC. So in this circuit we have inductor as well as capacitor. This inductor is available means the current is lagging. If capacitor is available means the current is leading. The analysis of RL circuit, RC circuit available in the previous video. Link is available in the description box. You can view that. So in this we have both inductor and capacitor. So based on the value of inductor and capacitor, the current may be lagging or leading. Based on that we have three different cases are available. So first one is XL equal to XC. In the case 1, this capacitive reactance equal to inductive reactance. Both are equal. We assume that there are three different cases. Case 1 is both are equal. If both are equal, it is act as a pure resistance. If XL equal to XC, the circuit is like a resistance because capacitive reactance is cancelled by the inductive reactance. That is leading lagging is cancelled. So that it is act as only resistance. If it is resistance mean current is in phase with the applied voltage and power factor is also unity. If XL equal to XC, both the effects are got cancelled. The current will be in phase with the voltage and power factor become 1. So based on that the phasor diagram is available. The current is available here. This is the voltage across the inductor. This is the voltage across the capacitor. Both are equal. Both got cancelled. So that only the voltage is available. VL equal to VC, XL equal to XC. So that voltage and current are in phase with each other. It is like a resistive circuit, simply a resistive circuit. So there is no phase angle. So the power factor also 1. Now we'll go to the second case. In this the XL is greater than XC. Capacitive reactance is lesser. Inductive reactance is more. Right? Here the capacitive reactance is less and inductive reactance is more. In that case it will act as a RL circuit. Because of inductive reactance more inductive reactance, it acts as a RL circuit. If RL circuit, inductive circuit means current lagging the applied voltage. Current is lagging. So the power factor is also lagging. So in the based on our condition assumption, inductive reactance is more than the capacitive reactance, so that it acts as a RL circuit. If it is RL circuit means the current is lagging the lag begins the voltage, so the power factor is also lagging. So based on that the phasor diagram is available. The current is taken as the reference vector. The voltage across the resistor is in phase with the current. Right? This VR is in phase with the current. This voltage across the inductor is leading. That is current is lagging means the voltage is leading. Similarly, the voltage across the capacitor. The current is leading means voltage is lagging. In case of capacitor, current leads but the voltage is lagging. See this magnitude, this VC is lesser. VL is more. VL is greater than this VC. Right? So the difference between these two, VL minus VC, is available here. In that VL, if you subtract VC, the remaining voltage is available. So the vector sum of this VL minus VC and VR is nothing but the total voltage. Because voltage is leading, we are getting the angle also in a leading. Pi in a positive value. So V is the vector sum of this VR and VL minus VC the whole square. So here the current is taken as reference, the voltage across the resistor in phase with the current, the voltage across the inductor leads the voltage across the capacitor lagging the voltage. So the difference between these two is nothing but VL minus VC, because VC is lesser, VL is more. The sum of these two voltages is nothing but the total voltage V. So that is given here. So based on that the waveform is available. This is the voltage, starts at 0 degree. Here RL circuit, so current is lagging. So current starts after some time, that is a pi angle. After pi angle only the current starts. So the current lags the applied voltage by V. So there is a lagging between current and voltage, that is current is lagging by angle of pi. So the current waveform, this voltage waveform. So based on that we'll have the impedance diagram. So this is the resistance in phase. This capacitive reactance is lesser, inductive reactance is more. So the voltage is leading, that is current is lagging mean voltage is leading. So that we are getting in a upward direction. So this is nothing but the difference between XL minus XC. The sum of these two is nothing but the impedance, R plus X, JX. J represents 90 degree. Right, this X is nothing but XL minus XC, and pi is positive because voltage is leading. Right. So the reactance here is nothing but difference between inductive reactance and capacitive reactance, XL minus XC. So from this diagram we can easily write that V square equal to VR square plus VL minus VC the whole square from the phasor diagram. From the previous phasor diagram we can write this equation from this diagram. V square equal to VR square plus VL minus VC the whole square. So that we can go for further analysis. So VR is nothing but IR, I into R. VL is IXL, VC is IXC. So the I is available everywhere, so take outside. I square equal to R square plus XL minus XC the whole square. This is V square. We take square root on both sides, so that V equal to I square root of R square plus XL minus XC the whole square. So this term is nothing but a impedance Z, that is V by I, Z equal to V by, bring this I in the denominator, so Z equal to V by I. So the impedance of this case XL greater than XC means square root of R square plus XL minus XC the whole square. This is the impedance for the second case. Now we'll go to the third case. In this, capacitive reactance is more than the inductive reactance. XL is greater than XC. So this circuit will act as a RC circuit. Capacitor, resistor and capacitor circuit. Capacitor circuit means current is lagging, leading the voltage. Current is leading the applied voltage, so the power factor also leading. Right? So due to more capacitive reactance, the circuit acts as a RC circuit. So the current is leads the applied voltage and power factor is 0. Power factor is leading. So based on that we have phasor diagram and waveform. So this is the reference vector current. The voltage across resistor is in phase with the current. So this is the voltage across the inductor, lesser value. This is the voltage drop across the capacitor, more value. Right? XC is more than VC. So the difference between these two, this is lesser, difference between these two is VC minus VL. Because current is leading but the voltage is lagging here. Voltage lags, current leads. So that it is drawn in downward direction. So vector sum of these two, VR square plus VC minus VL square is nothing but total voltage V. So the angle also negative, the voltage, the resultant voltage also available in the negative direction, because capacitor circuit current is leading but the voltage is lagging. Voltage is lagging. So this is the resultant voltage. Now we'll see the waveform. This is the voltage waveform. Starts at 0 degree. Current starts leading, right? So current start earlier. Before starting the voltage, current start earlier with an phase angle of pi. So there is a phase difference between current and voltage is pi, that is leading. Current starts earlier. In previous case RL, the current start later. Here current start earlier. So there is a phase difference of pi. Now we'll go to the impedance triangle. So this is the resistance. Because of voltage is lagging, so that it is drawn in downward. This is nothing but Xc minus XL. Because Xc is more, XL is less, so that Xc minus XL. Vector sum of these two is impedance, R plus Jx. So the X is nothing but Xc minus XL. So the pi is also negative. So now we discuss the RLC series circuit. Here the three cases available. XL is equal to Xc. Both inductive capacitive reactance are equal. In the second case, capacitive reactance is lesser, inductive reactance is more. That act as RL circuit. In third case, capacitive reactance is more and inductive reactance is less. That act as RC circuit. We analyze the phasor diagram, waveform as well as impedance triangle for all three cases. Thank you. Welcome viewers. In this we will see the parallel AC circuit. This parallel AC circuit means the impedances are connected in parallel. The combination is excited by the AC source, then it is called a parallel AC circuit. The series circuits are available in separate video. The link is available in the description box. You can see that. So in this parallel circuit, we have two branches available. In branch 1, resistance and capacitor are connected in series. In branch 2, resistor and inductor is connected in series. These two branches are connected in parallel. It is excited by the voltage V equal to Vm sin omega t. This is the current I, total current. That is due to parallel, it is split into I1 and I2. So we have two branches available. These two branches are connected in parallel. Now we'll see what is the reactance, what is the impedance of these branches. So the branch 1 having resistor and capacitor. Branch 2 having resistor and inductor. So the resistance of the branch 1, Xc1 equal to reactance. Reactance of the branch 1 Xc equal to 1 divided by 2 pi Fc1. Because of capacitor, this is the reactance. This 2 pi can be written as omega. So that 1 divided by omega C1. The reactance of the second branch is XL2. Second branch containing the inductor. So 2 pi F L2. That is omega into L2. Right? The branch 1 capacitor termed as C1, in branch 2 inductor termed as L2 for the simplification purpose. So based on the reactance, we can able to calculate the impedance. The impedance Z1 is nothing but R1 square plus Xc1 square. Resistance and capacitance. In branch 1 we have resistance and capacitance. Then what is the phase angle pi 1? Tan inverse Xc1 by R1. Similarly, the impedance of the second branch Z2 equal to square root of R square plus XL2 square. Second branch containing resistance and inductance. Similarly, what is pi 2? Tan inverse XL2 divided by R2. Now we will go to another three terms: conductance, susceptance and admittance. What is conductance? It is reciprocal of resistance. Resistance means opposing the flow of current. Conductance means it will allow the flow of current. What is susceptance? Susceptance is nothing but the reactance. The reciprocal of reactance. Reactance means it will that also oppose the flow of current. Susceptance means it will allow. What is admittance? That is reciprocal of impedance. Reciprocal of impedance is nothing but a admittance. Now we will see these three terms for this branch 1 as well as branch 2. For branch 1, conductance G1 is written as R1 divided by Z1 the square. Susceptance B1 is written as Xc1 divided by Z1 square. It is positive because in the inductive circuit, capacitive circuit, it is positive. Then admittance is nothing but Y1 equal to square root of G1 square plus B1 square. So it is nothing but this is the resistance, reactance, impedance. It is a reciprocal. It is a reciprocal of the resistance, reciprocal of the reactance and reciprocal of the impedance. So that similarly we are writing this formula. Similarly for branch 2, the conductance G2 equal to R2 divided by Z2 square. then susceptance B2 equal to XC2 divided by Z2 square is negative because of inductance. Then admittance Y2 is square root of G2 square plus B2 square. Now we'll find the total conductance. Total conductance is G equal to capital G equal to G1 plus G2. Total susceptance is B1 minus B2. Total admittance is G square minus B square. This is G square minus B square for the entire circuit. Similarly, the branch current I1 equal to V into Y1. I2 is V into Y2. Total current is V into Y. The phase angle can be calculated tan inverse B by G. If it is lagging, if B is negative, it will lagging. Similarly, cos pi is nothing but G by Y. So in this video, we analyze the parallel RLC circuit. Two branches available. We calculated impedance and reactance for branch 1 and branch 2. Then we also calculated inductance, susceptance, admittance of branch 1 as well as branch 2 as well as the total for the total circuit. Thank you. Welcome viewers. In this video, we will see the phasor representation of sinusoidal varying alternating quantities. This phasor representation is the more convenient form. We can easily analyze the quantities rather than equation and waveform. In order to solve the complex problem, this phasor diagram is very important. We can easily understand the alternating quantities by using the phasor diagram. Now we'll see the phasor diagram. So this is a sine wave, sinusoidal sine wave. We will taken as a voltage. The sine wave is nothing but the initially at point 0, at the angle 0, it is 0, then keep on increases and reaches the maximum value at 90 degree. Again it keep on decreases, reaches the 0 at 180 degree. Again increases in negative direction and reaches the maximum value at 270 degree. Then decreases in negative direction and reaches the 0 value at 360 degree. So it's keep on changing, alternating. So that can be represented as a circle. So this is the point 0, right? So initially it is 0, then keep on increasing, then keep on decreasing. So this is nothing but equivalent to the positive half cycle. Again it is increasing in reverse direction, increasing in the opposite direction, then decreasing. So this can be treated as a negative half cycle. So here the alternating waveform that can be represented as a phase diagram, we can easily understand. That is, it is keep on rotating, the voltages keep on rotating, increasing, decreasing, again increasing, decreasing in positive direction as well as negative direction, right? So here we have the point 0, 0 to P. So that is equivalent. This line is drawn, equivalent line is drawn that intersect at this point. So this is the point, nothing but the point P. So this angle is phi, the same angle, this angle also phi, both are equal, right? So here when the voltage increases, the angle also increases, here also angle also increases. So this angle can be easily measured from the phasor diagram itself, right? So the entire sine wave can be represented as a phasor diagram for easy understanding purpose. So this EM is nothing but the maximum value of the alternating quantity. This EM is the maximum value of alternating quantity, right? So in order to satisfy this phasor diagram, there are some conditions available. Any alternating quantity, either voltage or current, can be represented by rotating phasor. Rotating phasor is nothing but this diagram. This is a rotating phasor. Either voltage or current can be represented as a rotating phasor for satisfying the following condition. The following condition should be satisfied. Then only the sinusoidal quantity, either current or voltage, can be represented by the rotating phasor. What is the first condition? The magnitude of rotating phasor should be equal to the maximum value of the quantity. So the magnitude of rotating phasor should be equal to the maximum that is available. So this is the maximum value. So this is also maximum value. So both are equal. So we can represent this as a rotating phasor. The sine wave can be represented as a rotating phasor because the maximum magnitudes are equal. The second point, the rotating phasor should start initially at 0 and then move in anti-clockwise direction. So here also we are moving in a anti-clockwise direction. The second condition also satisfied. So we are moving in a anti-clockwise direction like this. Starts at 0, we are moving in anti-clockwise direction. Then third condition, the speed of rotating phasor should be in such a way that during its revolution, the alternating quantity completes one cycle. Right? While moving the rotating phasor, while moving on full rotation, the alternating quantity should complete one cycle. So that is also is available. That is also satisfied. See this. While completing this one circle, one rotating phasor, here one complete cycle is completed. A positive and negative half cycle is completed. Right? So the entire cycle can be represented as a one rotating phasor. So third condition also satisfied. Now we'll go to the in phase, out of phase, the phase angle between the two quantities. Now we'll see the in phase and out of phase relations. So the phase is nothing but the fraction of time period that elapsed from reference or zero position. That is the phase is nothing but elapsed from the reference. How it is deviated from one quantity, how is another quantity is deviated is nothing but a phase. In that the first type is in phase. What is in phase? Two alternating quantities are said to be in phase if they reach their zero value and maximum value at the same time. If two alternating quantities are there, both are starts at the same time and ends at the same time. That is, the zero value as well as maximum value is the same time in, that is treated as a in phase. The starts and end at the same time. Right? So that is represented in this waveform. Now consider the two waveform. I1 equal to Im1 sin theta. I2 equal to Im2 sin theta. What is this? So this is represented in a waveform. This is I1. This is a waveform I1. It's a sine wave. It starts at 0 degree. This I2, only the amplitude is maximum. Amplitude is more. That also starts at 0 degree and ends at the maximum value and reaches the maximum value also same time. There is no phase difference. Both waves are starts at 0 degree itself. Both reaches the maximum at the same time. Again reaches the zero value same time. Again reaches the maximum same time. Again reaches the zero value same time. So this is called a in phase. There is no phase angle between these two waveforms. That also analyzed from the equation. See this sin theta, here also sin theta. There is no more additional angle available. It means that these both are in the in phase, right? So this is the maximum value of first waveform, the maximum value of second waveform. So that is represented in the vector diagram. This I1 and I2. See, both are available in the same line. There is no deviation. I1 and I2 are available in the same line, right? So from this waveform we can analyze that. From the above waveform it is clear both I1 and I2 reaches the 0 and their maximum value at the same time, even though they have different maximum value. The maximum values are different, but the 0 and maximum values are reaches at the same time, right? So it is also referred as both current are in phase, meaning that no phase difference between two quantities. It also represented by the vector diagram, right? There is no phase angle between these two quantities, right? So that is also represented by this vector diagram. Now we'll go to the out of phase, the second type. What is out of phase? Two alternating quantities are said to be out of phase if they do not reach their zero and maximum value at the same time. Maximum value and zero values are not reached at the same time. The phase difference between these two quantities are represented in two different forms. One is lag or lead, right? In previous case, both zero value and maximum value reaches at the same time. Here it's not at the same time. It may be lead or lag. It may be the angle will be the leading or angle will be lagging. So based on the two types available. First we will see the lagging. What is meant by lag? The lagging alternating quantities is one which reaches its maximum value and zero value later than that of other alternating quantity. Later. So the lagging means one alternating quantity is lagging with the another quantity. The second quantity will reach the zero value before, after that. The first quantity will reach the maximum value. After some time only, the second quantity will reach the maximum or zero value. So there is a later. So it will reach the maximum of zero value later. So that it is called a lagging. So that is represented by minus pi. I2 equal to Im to sin omega t. So that starts at 0 degree like previous case. But I1 equal to Im1 sin omega t minus pi. Right. So the minus refers lagging. Right. The pi angle. This pi angle is lagging between I1 and I2. I1 reach the maximum value delaying with an angle of pi. Right. So that is represented in the waveform. See this is the I2. The I2 starts at 0 and is going, keep on going, sine wave. It's like a normal waveform, 0. But I1 starts after pi. After pi angle only the I1 starts. There is a delay. There is a delay of starting with the current I1 with I2, this pi. So due to this delay it is called a lagging. So this angle is subtracted because after pi only the I1 is starts. So that is represented by this negative sign, that is indicated as a lagging. So this is the lagging angle between I1 and I2. I1 starts at 0 but I2 starts after some angle, that is called pi. So this is the lagging angle. So due to the delay it is subtracted and termed as a lag. So that also represented by the vector diagram. So this is I2 normal 0 degree, it starts at 0 degree. But I1 starts later on, so that it is in the downward. If it is starts earlier, it will go to the upward, positive. This will be negative. So this is the angle between this pi is the angle between I1 and I2. Because it starts later, there is a delay. That's why it is given in a downward direction. If it is lead, it will given in the upward direction. So from the above waveform, it is clear that I1 reaches its maximum value and zero value with a phase difference of pi after I2 reaching. So the I1 will reach the maximum and zero value at a delay of pi. So that I1 lagging the I2. So I2 reaches normally, but I1 reaches after pi. Now we will see the second type, leading. So the leading is nothing but leading alternating quantity is one which reaches its maximum value and zero value earlier. Before reaching the one quantity, another quantity will earlier than the other alternating quantity. The previous case it is later, now it is earlier. So that is called a leading. So it is represented by the equation I2 equal to Im2 sin omega t. So it starts at 0, there is no delay. But I1 equal to Im1 sin omega t plus pi. Right? So it will start earlier, plus pi. If it is minus pi means later, but it is plus pi. So it starts earlier. So this plus indicates this waveform starts earlier than this second waveform. This plus indicates that it is a leading. So that is represented in the waveform. See this I2 starts as a normal, it starts at 0. But I1 start earlier. Before angle of pi, the I1 starts. Before starting I2, I1 starts earlier with an angle of pi. So that is indicate this is the leading. I1 is leading with the current I2 with an angle of pi. In previous case, lagging I1 starts later. Here I1 starts early. So due to this earlier, this see the phasor diagram. This is I2. This starts at 0, but I1 starts with an angle of pi. It is leading, so that it is given in the upward direction, anti-clockwise direction. upward direction. Lagging means will go to downward direction. So this is pi is the angle between I1 and I2. I1 is leading with pi with the current of I2. So that is given in a statement. From above waveform, it is clear that I1 starts already and reaches maximum value before I2. So the I1 is starts earlier, that is I1 is leading the I2. I1 leads the I2. So that is the given by the angle plus pi. So from these two we can able to note down that two vectors are said to be quadrature. Quadrature means exactly 90 degree. There is a 90 degree phase difference between the two vectors if it is quadrature. Two vectors are said to be anti-phase, means 180 degree. In phase means 0 degree. So anti-phase means 180 degree. So in phase means 0, anti-phase means 180 degree, quadrature means 90 degree. So in this video we discuss about the phasor diagram of a sinusoidal waveform. Two types, in phase, out of phase. In that again lead, lag. Thank you. Welcome viewers. In this video we will see the complex J operator. That is, it is used to indicate the complex number having real term and imaginary term. That is a vector quantity. A vector quantity has both magnitude and direction. So that is represented in a two plane as shown below. So this is nothing but a complex number. Now consider A equal to A plus JB. What is A? A is the real term, B is the imaginary term. So that is represented in this graph. So as the x-axis, the real term is available. This is the y-axis. In that the imaginary term is available, A and B. So this is B, the equivalently it is drawn here. So the vector sum of these A and B is nothing but the resultant vector M with a magnitude of A. So A is the nothing but vector sum of small a and b. A equal to A plus B. The A available in the x-axis, that is the real axis. B available in the y-axis, that is called a imaginary axis. The sum of these two is the resultant vector A. So there is a phase, there is an angle between A and B is theta. So what is that theta? Is represent the angle of vector A. Pi is the angle of vector A. And also some more description given. The A is nothing but horizontal component or vertical or active component or phase component. It's a real term. A is the real term. It's also called as horizontal or active or phase component. The B is the vertical component or reactive component or quadrature component. Quadrature means 90 degree. It's an imaginary part. So the A is the real term, B is the imaginary term. It also represented in the another two forms available, magnitude and angle. How will you find the magnitude from this way, from this equation? From this A equal to A plus B, the equation available for this equation, how will you find the magnitude and phase angle? Magnitude equal to square root of A square plus B square, that is square root of real term square plus imaginary term square. So it will give the magnitude. Similarly, the angle alpha can be, this alpha, theta are both are same. Tan inverse B by A, that is imaginary term divided by real term. So normally it is called as this is a rectangular form. This is the polar form. That also we will see later. It's a rectangular form and polar form. The rectangular form contain real term and imaginary term. Polar form contain magnitude and phase angle. How will you find magnitude and phase angle? Simple. This is a square root of A square plus B square. Angle is tan inverse B by A. So for our convenience solving the problem, we can either use this rectangular form or this polar form. We will see how to convert the rectangular and polar form. Now we will see about what is the J operator. What is this J operator? Some more details about the J operator. J equal to square root of minus 1. This is a value. Value of J is nothing but J equal to minus 1. If you square on both sides, you will get J square equal to minus 1. That is J into J is minus 1. right. So, during the problem we can use two values, j square equal to minus 1 or j equal to square root of minus 1. What is this j indicate? This indicates anti-clockwise rotation of vector by 90 degree. If j is available, we can assume that we can see that it is rotating in anti-clockwise direction with 90 degree. If j square is available, it is rotating the anti-clockwise with 180 degree. If j cube is available, is 270 degree. So 90 degree will increase. J power 4 means it is 360 degree. Right. So the j represents 90 degree. J square, j cube means keep on increasing. So this minus j indicates clockwise rotation of 90 degree. So far we discussed only plus j, j square, j cube. If it is j minus j, j means anti-clockwise, minus j means clockwise rotation. Then how will you find the value 1 divided by j? We cannot find 1 divided by j, so that in order to convert in the convenient form, it is divide and multiplied and divide by j. This 1 by j is multiplied and divided by j, so that the originality will not change. So 1 divided by j into j divided by j. So that is nothing but j is available here, denominator 2j available. So j divided by j square. What is j square? J square is minus 1. So j divided by minus 1 is nothing but minus j. So we can simply remember 1 divided by j is nothing but minus j. So this is the detail about the j operator. J means anti-clockwise rotation by 90 degree. If j square, j cube mean the 90 degree will be added. Minus j means clockwise rotation. 1 by j means it is minus j. Now we will go to the rectangular and polar form. So the vector can be represented in polar form or rectangular form. What is polar form or rectangular form? A equal to 2 plus j3 is the rectangular form. Real term plus imaginary term with j operator is a rectangular form. So this is nothing but polar form. How will you find this magnitude and angle? Magnitude is calculated as square root of a square plus b square. Real term square plus imaginary term square. How will you find the angle? Alpha equal to tan inverse 3 by 2. That is imaginary term divided by real term. So this is represented by magnitude and angle. Magnitude is 3.606, angle 56.31. So this is a polar form. So both are equal. Here represented with real term and imaginary term, rectangular form. Here represented with magnitude and angle for the polar form. Why we are using these two different form? So during the manipulation, that is during addition and subtraction, we can easily use the rectangular form, because we can easily add these two terms, add or subtract. During multiplication and division, the polar form can be used. Why? We have magnitude angle, so that we can easily use with the polar form. So based on that, we will go to the some example problems. So first we will see the example 1 for addition. So already we discussed, for addition and subtraction we can use the rectangular form. Subtraction, multiplication and division we can use polar form. So here two vectors available, a equal to 2 plus j3, b equal to 4 plus j5. The question is we need to add both the vectors. So it is already in the polar, in the rectangular form. So you can easily add 2 plus j3 plus 4 plus j5. We need to add both the real terms, 2 plus 4, 6. Both the imaginary terms, j3 plus j5, it is j8. So it is easy, it is easy to add two vectors when it is in a rectangular form. And one more question is, we need to find magnitude and phase angle, that is polar form. How will you find the magnitude? Square root of this real term square plus imaginary term square, 6 square plus 8 square. So that is equal to 10. Then how will you find the phase angle? Tan inverse imaginary term j, real term 8 by 6, 8 divided by 6, imaginary term 8, real term 6, that is 53.13 degree. So in this problem, two vectors available in a rectangular form, that is added. So with rectangular form, that can easily added. Real terms should be added and imaginary terms should be added. From that we calculated magnitude and phase angle also. Now we will go to the second problem for subtraction. So here another two vectors available, A equal to 2 plus J5, B equal to 4 minus J2. The first question is A minus B. We need to subtract these two vectors. A is nothing but 2 plus J5 minus of, we need to put minus commonly, 4 minus J2. Now multiply this negative inside, so that minus 4 plus J2. Now we can add both the real terms. 2 minus 4 is minus 2. J5 plus J2 is J7. So it is easily subtracted when it is in the rectangular form. Just we need to add both the real terms and both the imaginary terms. And one more question is available. We need to find the magnitude. How will you find magnitude? Square root of real term square plus imaginary term square. Real term is minus 2, imaginary term is 7. So the value is 7.28. Then how will you find phase angle? Tan inverse imaginary term by real term, B by A. So 7 divided by minus 2. So it is minus 74.055 degree. So here two vectors available, two are subtracted easily with the rectangular form. One more question, from that we calculated magnitude and phase angle also. Now we will go to the third problem. The third one is the multiplication. The two vectors available, A equal to 2 plus J3, B equal to 4 minus J5. We need to multiply these two and we need to find the magnitude and angle. So it is in a polar form, so it is a rectangular form, so we cannot multiply easily. We can be possible to multiply, but it is easy to convert into polar form, then we will go for the multiplication. This rectangular form also multiplication is possible, but it is easier to convert into polar form for the multiplication. So how will you convert this polar form? This magnitude of A is nothing but square root of real term square plus imaginary term square. Real term is 2, imaginary term is 3. So after simplification, what we got? 3.606. What is the angle here? Tan inverse B by A, that is imaginary term divided by real term, 3 by 2. It is 56.31. Now it is represented A equal to 3.606 with an angle of 56.31. So this is the real term, this is the rectangular form. Now that is converted into polar form. So this one can be done by in the calculator also. In the calculator directly you can convert from rectangular form to polar form. This is the normal calculation method. In calculator it is available directly. Similarly the second vector is 4 minus J5. First we will find the magnitude, that is square root of 4 square plus minus 5 square. Real term square plus imaginary term square. So the value is 6.403. Angle is tan inverse B by A, imaginary term divided by real term, minus 5 by 4. So it's minus 51.34. So due to negative we got negative sign. So that can be represented magnitude 6.403, angle 51.34. So this is the rectangular form now converted into polar form. So these two can be multiplied easily. These two also can be multiplied, but it is easy to convert into polar form, then we'll go for the multiplication will be easier. So A into B. So A is nothing but 3.606 with an angle of 56.31. B is nothing but 6.43 with an angle of minus 51.34. Then how will you multiply these two? You have to multiply these two magnitudes. For multiplication, magnitudes are multiplied. So 23.089. What about the angle? Angle should be added together. For multiplication, we need to multiply the magnitudes and the angle should be added. 56.31 is added with minus 51.34. Already negative is there, so it becomes subtraction. So it is 4.97. The general format is we have to add both the angles for multiplication. So now we got 23.089 with an angle of 4.97. The multiplication of A and B. Now we will go to the next example, the division. This is the first vector, A equal to 4 minus J2. That will now convert into polar form. The magnitude of A is square root of A square plus minus 2 square. So the value is 4.472 magnitude. Then angle is tan inverse minus 2 by 4. Imaginary term divided by real term. Minus 26.565. So it is represented in the polar form 4.472 with an angle 26.565. So this is the rectangular form, now that converted into polar form. So another vector, B equal to 2 plus J3. Real term is 2, imaginary term is 3. So the magnitude is nothing but square root of 2 square plus 3 square. So the final value will be 3.606. The angle tan inverse B by A, imaginary term divided real term. 3 by 2 is 56.31. Now it is represented in the polar form 3.606 with an angle of 56.31. Now this rectangular form of A and B is now converted into polar form of A and B. Now we will go for the division, A divided by B, A divided by D. So this is the vector A and vector B. How will you divide? You have to divide these two magnitudes. Multiplication will be we multiplied two magnitudes. Similarly here two magnitudes are divided. What about the angle? Angle should be subtracted. In previous case the angles are added together. Now the angle should be subtracted. So this angle, while this angle going into the numerator, it become minus. So both are minus, so it become minus 82.875. The multiple division of these two is 1.24. So this is the final value, A divided by B, right? So for multiplication the magnitudes are multiplied, the angles are added together. For division the magnitudes are divided and angles are subtracted. So in this video we discuss about the complex J operator, then what is meant by polar form and what is meant by vector form, and we discuss the 4 different examples: addition, subtraction, multiplication and division. Thank you.